Okay, well, let's see if I can start by sharing something, possibly a screen. Even a Chrome tab? That one feels like a good one to share. Okay, all right, so let's see if I can. All right. Okay, so the thing I wanted to start this out is just with a welcome to our fancy little workshop on larger than memory data workflows with Apache Arrow. And I'm going to see if I can, there we go, I've got that in a widescreen mode so that I can actually see the menus. So we have a website, and I'm going to jump over to the slides so that I can have the, aha, there we go. Yay, I always like to start with this. Hi, larger than memory data workflows with Apache Arrow. So hopefully you're in the correct place. I am Danielle Navarro. The other two instructors for this workshop will be Jonathan Keane and Stephanie Hathlet. They will be handling chat stuff. So anytime you get confused or bored, or you just decide you don't like me, you can kind of comment in the chat, and they will try to handle things as well as possible. There are also breakout rooms. So if you hit the little icon there with the 4 buttons, you can disappear from this room and chat with them in the breakout room to deal with whatever issues are coming up over there. I know nothing about the breakout rooms. I'm not going to be doing the breakout rooms. I will be the person who sits here talking pretty much continuously and annoyingly for about 3 hours, but I will try and make this as a little interactive as we go. Some general housekeeping that I wanted to mention. Oh, actually, I will pass over to Jonathan.
One note about the breakout rooms, message either Steph and I if you want to go into one. We don't actually get like a notification if you go into a room. So you might be sitting there alone if you don't message us first. But we'll be happy to jump over and help out or answer questions or anything like that.
Excellent point. So that actually gets foreshadows nicely a point that I wanted to make just as a general thing for everyone. We're a bit, this is a new platform for all of us, so we're all a bit inexperienced with dealing with it. So some general requests to, if you can all be a bit patient, but if something goes wrong at the same time, please feel free just to, to ask in chat, and you can unmute yourself. If something's gone awry, feel free to unmute yourself to just, hey, ask questions, make sure that we actually do notice you. We will be doing our very best to notice whenever somebody uses the little raise hand icon and things like that. Okay, the website associated with this tutorial is at arrowuser2022.netlify.app. And one of the reasons I wanted to emphasize this at the beginning is that essentially everything you need associated with this tutorial is somewhere on this website. So that if, by some horrible twist of fate, all 3 of us die in the first 30 minutes of this tutorial, you will, not wishing any horrible things to happen to my lovely co-instructors, there will be material that you can continue on with, and it will actually be pretty comprehensive and help you through everything else. So just to give you a bit of a sense of it, I will kind of go, okay, well, I'll just click on the link there, and so go, okay, well, I can browse the site and go, oh, look, here we have an entire written tutorial that says, packages and data. So if I wanted to run through the whole tutorial, It's got a, hey, here's a thing that says, here's the packages that you would need to run everything. This is, loading stuff. Here is a complete, data dictionary for the major data set that we'll be using, and bits and pieces and checks to make sure that things are working and so on. But we can go back and go over here to say, hey, here's the written tutorial. So the content that I'm going to go through on the slides is mirrored in a written tutorial that is hopefully pretty comprehensive. It's got all the content is in there. It has exercises with solution sets and things like that. So if at any point you kind of go, okay, I don't particularly feel like following along, that's okay. You can always pick up things later on. So it's all there. And that, I think, takes pressure off of all of us, me included, because this is my first time ever teaching anything Arrow related, to be perfectly honest, which is terrifying. It gives us a bit of a chance to kind of go through this in a no pressure sort of way. You can come back to this later on, and you can check things out. Okay, so up on the website, there are also links to the slides. So I'm going to go back to the slides that I was on. Okay, so the slides that I'm working off are up on there. The GitHub repository has everything that you need. In fact, I'm basically working from this GitHub repo, and so on. Okay, so hopefully that is the bare minimum required to get a sense of what all the background resources are. The structure of the tutorial is going to be approximately like a four. It's in written form. It's a 4-part series. So we're going to do a Hello Arrow, where we're just going to dive in and start doing things, and then I'm going to go backpedal a little and talk about what is Arrow, why do we care, and so on. We're then going to go into a section on data wrangling, some things around data storage, and then finish up with a few advanced topics. You'll see that in the slides as we go, it's broken down in a bit more of a fine grain kind of way, and that's largely because it'll give us more opportunities just to stop and take breaks as we go. I don't particularly fancy talking for 3 hours straight, and I'm not sure that anybody's really keen on listening for 3 hours straight without any breaks. So we'll let things kind of, go at whatever pace they come up at. And yeah, all right. So if you do want to type along, you'll notice that here on what must be like slide 4 or 5 or something, there is a copy of the quick start guide. This is also on the website itself, and this is your okay, I actually do want to go along. Yes, I want to follow along. I want to make sure I've got everything set up properly, and here's the fastest way you can possibly get on with that. So first line would just be install, download the R project for this repository, from GitHub, install that in your local machine to wherever you like. Remotes install deps command will install all your dependencies. So hopefully that's always the trickiest part, but with any luck, that will all go completely smoothly, and all of the packages that you need will install perfectly. This will contain everything you need except for the data set. The data we're going to work with comes in 2 forms. There's one very, very large data set, which is 69 gigabytes in size. And I'm told that there are people who live in places where this is actually a feasible download size, that you can actually do this, and it doesn't take overnight. But where I live, that's an overnight job. So if you want the 69 gigabyte version, great. There are instructions for that on the website. I'm not going to try and do that on the fly in the workshop. There's a smaller version, which is basically 1,000th of the size, which is manageable even if you have a terrible internet connection like me. So you can just basically download the file directly from GitHub, unzip it, and you will be good to go. And we'll talk a little bit more about what's in that file as we go. All right. Hopefully that will be enough to let anybody get started if that's what they really want to do. Cool. All right. So as always, if we're doing anything in R, we need to load some packages. The one that we're going to care most about, oddly enough, is going to be the Arrow package, but almost everything that we do data analysis wise with Arrow is also going to involve dplyr, so we want that loaded, and a whole lot of other things are going to come along for the ride as we go along. Again, this is fairly uninteresting preliminaries, so let's go straight into Arrow. All right. Arrow, as most of you will be aware if you're taking, this workshop, is this tool that we use for analyzing large data sets, among other things. So the data that we're going to be using throughout this workshop is relatively well known, but if you don't know it, it's the New York City taxi cab data. And as I mentioned earlier, the full version is 69 gigabytes in compressed Parquet format. So it's not a tiny little thing. It's comprised of 158 separate Parquet files, and you can open it just fine with, in R with this open dataset file. So on my machine, I've got a copy of it located at dataset/NYC taxi. And when I go to open it, I will see something like this. I get output that says I'm looking at a file system dataset with 158 Parquet files. What that's telling me fundamentally is my copy of Arrow has scanned the directory that contains all of these data files and has had a quick look and said, okay, these are the files that we need, and knows something about the structure of the data that's buried in these files. It has not loaded them into memory. It can't, because as you'll see in a moment, that data set is too large to load into memory, but it at least knows what we're looking at. It also prints out the schema associated with the data. So it tells you what your variable names are. So this is a data set that has essentially one row in a table per taxi ride. So we've got the when did the taxi pick the rider up? When did they drop them off? How many passengers were there? How long was the taxi ride? What was the longitude and latitude? That's often a missing field, but if it's there, then it tells you where exactly you're picking them up from. A more reliable field in the data, if we just pop down to the bottom here, is something like the pickup location ID, which is a numeric code that tells you something about, it's an approximate location, so it's which out of the 265 taxi zones in New York City, the pickup or drop-off took place in. And there's a whole lot of things to do with payment, which apparently, this being the United States, this also involves things like tipping, which I entirely do not understand, but apparently is a thing that people do. So this gives you a bit of a sense of the data, at least what is involved. Thank you, 20%. I will remember that. I'm hoping never to have to travel again, except I know that I will. Right. Okay, so if I'm doing this from the command line, I would like to be able to explore this thing as if it were a regular data frame in R, right? And to an extent, I can do that, right? So I can start typing commands like nrow, right, to calculate the number of rows in this table. I'm actually, I'm not going to make too much of a habit of I should be able to, can I really? Okay, hold on. This is the bit where I discover that I am, oh, okay, I see I have to, I have to stop sharing there, and then I have to start sharing again. That seems slightly suboptimal. There we go. Okay. So, okay. I'm not going to spend huge amounts of my life. Let's make this a same size. There we go. Okay. So we're not going to give you at least a little bit of a sense of how this works live. We should always do a tiny bit of live coding so that you can believe me that all of the stuff that you're seeing on screen is for real, right? So if I go, so I should already have everything loaded, but in case I don't, we'll go library arrow. Okay, apparently I don't, so that, and I'll probably, for the sake of my sanity, I don't need dplyr just yet. No, we'll need it in a moment. Okay. So I've got arrow and dplyr loaded. We'll go nyc taxi, open data set. And so we're looking for our sources. So on my computer, I've got this thing. I have a data set nyc taxi. So there should just be a folder there that does that. And let's have a look at what we've got. And it says, yep, okay. And so that's exactly the same output that you just saw. Somehow it feels more real when you're seeing the same thing in the console, but so let's now go, okay, well, how many rows does this table have? So let's go nyc taxi. It takes a little moment to do that because it does actually just have to check the metadata associated with the 158 Parquet files and tell me, yep, that's 1.7 billion rows of data. And I, as a humble social scientist, find that slightly mind-boggling because I'm still used to the idea of dealing with hundreds of rows or maybe even thousands. And yes, actually, that's a really good question, just picking that one up from the chat. The notation you're seeing in the slides, just in case you aren't familiar with it already, that's the base pipe. So whenever you see me doing that, rather than say that, it's still it's still a pipe, but there are subtle differences with the base pipe. It came out in, is it 4.1? I can't remember exactly, but anyway, there are some subtle differences between the base pipe and the Magritte pipe, but it doesn't make a difference for the purposes of this workshop. Okay. So I think the other thing I wanted to do is say, okay, well, it would be nice to have a look at least, the first few rows of the data. So if I go, let's go head, we'll just of nyc taxi. And this is sort of intuitively what I do in R. So if I do that, it doesn't help very much, right? This is what I automatically do. But all it's done is told me, oh, I've just subset my 1.7 billion rows to 6 rows, which is great. But usually when I'm typing head, what I actually want is show me the rows. Like I actually want to see the results, not just this little summary. The reason I'm doing this is that, so the reason I'm seeing this output is that this is the print method for an Arrow object. This is a table in Arrow. And what I really want to do is pull this thing from Arrow into R. So to do that, I need to call collect. So if I go head, what's the name of my data again? Oh yeah, NYC taxi. I know what I'm doing. You would think that having worked with this data set for months now, I would know what it's called, but no, I do not. Okay, so head, we'll pipe that to collect. Collect, we'll see a lot. Basically, that means, I'll talk about it multiple times, but for now, what this is going to do is grab this thing in Arrow, pull it into R. So let's do that. And now we have something that looks like a regular data frame or tibble. So we can see, yep, okay, we've got our vendor name. So that's, I think that's the name of the company that provides the record. Like, it's not anything that's super interesting.
Yep.
But we have a whole lot of other, yep. So, yep, and to answer the question in that, so collect is from dplyr. The reason I'm calling collect here, so you can do the same thing with, I think, as data frame. You could just pull it, like, coerce the Arrow table to a data frame, like that will work. But what we'll see repeatedly through the rest of the workshop is a super typical workflow is I'm just doing stuff in dplyr, and then at the end, I just want to have it all evaluate a query and pull it all back into R. And so using the dplyr collect syntax is just sort of normal. Oh, and at any point, I should mention, if you ever see Jonathan correct me on something, it almost certainly means that they're right and I'm wrong. I just want to make something super clear on this. Okay. Yes, Elliot, that's a really good point. So something regarding the NYC taxi being a file system data set and the results of that being a table is one of these distinctions I was hoping to sweep under the carpet until a little later in the workshop, but it actually does matter. So the super short answer is a file system data set is this thing that's on disk, hasn't been loaded into memory, and can be pulled into memory. Like it's loaded as needed to do the computations. Table is the thing that Arrow loads into memory when it loads something. That's a slight oversimplification, but it's close enough. And they both are tabular data structures. The main thing you want to recognize for now is that data sets are the big thing that you have on disk. Tables are the thing that gets that exists in memory. I'll unpack that a little bit more later on. They are different. They're treated as different objects in the Arrow package, and they have slightly different behavior. But for the most part, we sort of just pretend they're the same type of thing, even though under the hood, they're kind of different. All right. Hopefully that helps answer the question. Okay. Right, where was I? Okay, I think I will pop back over to the slides now. If I go back over to here, share options, give me my Chrome tab back. I want that. Okay. All right, so this gives you at least a little bit of a sense of what it's like working with Arrow objects. And that was me turning off my little space heater because it is 5:30 a.m. and it was cold, but now it's quite warm. So, okay, let's if we want to go about like doing actual data analysis, so most of the time we want to be, you know, doing something more interesting than just calculating number of rows and you know, looking at the first few rows of a data set. So the Arrow package is designed to make it easier for you to work with your large data sets in essentially the same kind of workflow that you're used to with your regular data sets. So that is, you get to use dplyr syntax, right? And so I'll talk a little bit more about how it does it, but essentially Arrow provides a dplyr engine. So you can, when you've got the dplyr package and the Arrow package both loaded, you can treat your Arrow objects, so your file system data sets and Arrow tables, as if they were data frames and analyze them using dplyr commands. So you can use filter, group by, summarize, mutate, collect, arrange, to do all of your kind of typical one table operations. You can do database joins. We'll go over some of that later in the workshop. There are some subtle differences between how normal dplyr operates and how the Arrow dplyr backend operates that mean you have to think of it as being a little bit like a database query. So rather than having all your operations happen in an eager way, so in dplyr, when you say filter, it will filter on the spot. In Arrow, it will wait. When you say filter, it will construct a query. And we'll add this to a query, but it won't execute the query until you say, you know, compute or collect. And this kind of lazy approach to queries is a handy way of making sure things are not unnecessarily wasteful. I'm not sure that there's such a thing as unnecessarily wasteful, but you get the idea. Okay, so that's the core of the idea. Let's have a look at this in practice. So here's a pipeline. So I would take the New York City taxi data set. I would filter it and say, okay, can you subset this so that I will have the year. I only want the data sets from the data from years 2017 to 2021. Let's add a grouping variable. So I'll group it by year. And then for every year, I want to count the number of so the total number of trips, so that's N. So I'll count the number of trips that were taken in that year. And I also want to count, and calculate the number of trips in which there were more than one passenger. So that I will call that my shared trips. So instead of counting all the rows, I only want to count the number of rows where the passenger count variable was greater than 1. So you'll notice I'm using here the sum function. I know that this is in some ways stating the obvious, but that's from base R. So although Arrow understands dplyr syntax, it will also do operations from base R. As you would expect, like it has to understand how to do basic calculations. So it needs to know how to do trigonometry. It needs to know how to do all sorts of operations that are fundamental to doing computations, because a lot of this stuff is not actually being done inside R. Okay, anyway, we're computing the number of, so the total number of trips, total number of shared trips, and then we're just going to do a mutate that says, okay, count the percentage of trips that are shared for each year. And so we go shared trips divided by all trips times by 100. And then we would collect that query and run that. And that will give us a result. So it will give us a tibble here, which is like 5 by 4. It says, okay, well, yep, there's, what is that? That's, you'd think I'd know this. So it's like 113 million trips that in 2017. About 28% of those were shared. There was only 30 million trips in 2021. I think there might have been some reasons why there were fewer taxi rides in 2021. And there's a bit of an effect there. You can see where the percentage of shared trips disappeared, in 2020 and 2021 for reasons we might find somewhat unsurprising. Okay, so now I'll give you a little bit of time if you want to have a go. For those of you who want to follow along, this is the part where you get to do a bit of do-it-yourself. There are some exercises here where you can try out the syntax yourself. I'll make the point, because the the slides template doesn't make this as obvious as it should be. That's a link. If you click on the exercises thing, it will take you to the relevant bit of the tutorial, and so you can actually see the text here from the relevant part of the tutorial. And we'll give this a little bit of time. We'll say 5 minutes to have a play with that. I actually don't know how long these things take, but feel free to ask questions. Let us know how things are going. And yeah. I'm just going to mute myself for a little bit. That is a really good question about why does that show as Boolean before the collect? I'm going to pass that one off to Jonathan in just a moment. Jonathan's having some technical difficulties. I feel like I half know the answer, but I'm going to give a really bad one. So I'm going to wait for somebody who's going to give a good answer rather than try to do a bad one. All right. So have most folks managed to finish up? I have no idea with timing. I mentioned this is the first time I've ever taught with this sort of material before, so there's got to be an easy way of poll. Here we go. I wonder if I just create a poll. This is silliest. Yes. No. Okay, I've added a poll there, just to sort of see if, hold on, there we go. Are we ready to continue? These sort of virtual teaching arrangements are very strange things. If you're not, just don't click on anything. I'll sort of wait until there are enough people saying yes, and then sort of head. Oh, is this going to show? Does this show live results or not? I can't.
Yes, only after you've actually answered the poll. So we're at 15 yes and 2 no.
Oh, okay. So I have to answer it as well.
Yeah. So.
Oh, there we go. All right. Okay. Got it. Technology. Fun. All right. Let's keep going then, because you know, that's a fun thing to do, really. Where is my okay? So if I go back there, all right. Okay, so hopefully that gives you a bit of a sense of, you know, how to do data manipulation with Arrow. The whole point of all of that was just to give you a bit of a sense that a lot of what you're doing with Arrow is the same kind of data analysis operations that you're already familiar with. Like, that's fundamentally the intent of the way the Arrow R package is designed. It's supposed to make the life of the data analyst a little bit easier. Yes, I'm dealing with almost 2 billion rows of data. Yes, that's more data than R can load into memory. Obviously, I'm doing this with something that's not an R object, and nevertheless, I'm analyzing it in a way that is super familiar to an R data analyst. That's the point, right? It's supposed to be analyst friendly. So hopefully you've at least gotten that much of a sense from it. Now what I want to do is sort of unpack a little bit for you some background, like what exactly is Apache Arrow? Why care? What's this all about, etc. So this is a bit more talky than last one. Okay, so I've stolen this little description from the Apache Arrow website, and I kind of like reading it as if it were a haiku. It's not the right syllables, but it feels very haiku-ish to me. Arrow is a multi-language toolbox for accelerated data interchange and in-memory processing. I like structuring it with that weird cadence because it has this, it makes the point that Arrow does three things. Like, there are three things going on here in the Apache Arrow project that are worth unpacking. It's multi-language toolbox, it does accelerated data interchange, and we use it for in-memory data processing. So let's go through what we mean by each of these things. First off, Arrow is a multi-language toolbox. So at a high level of abstraction, the Apache Arrow project defines a bunch of specifications, right? So if you go diving into the Apache Arrow website and you go to arrow.apache.org, you can dig in and you'll find a specifications page, and it will start having all of this stuff in there about, okay, this is how you lay out a tabular data structure in memory, and it will tell you this is where this block of data goes, and that's where that block of data goes, and so on. It's, you know, again, to my mind, as a social scientist, it's tediously low level, but of course, it's the kind of thing you actually have to care about. Those specifications are language agnostic. They don't actually care how they're implemented, right? And there are, in fact, multiple implementations that are independent of each other. So there's a C++, C#, Go, Java, JavaScript, Julia, and Rust all have independent implementations of these Arrow standards. And there is a whole lot of integration tests that are run to make sure that these different libraries stay in sync with each other, so that they are in fact implementing the same thing. Otherwise, bad things happen when you have different libraries that are ostensibly doing the same thing and aren't. So there are some efforts that are put in to ensure that these different systems are all doing the same thing. Not every language that does Arrow bothers to implement those standards directly. So R, Python, Ruby, and MATLAB, for example, do not directly implement the Arrow standards. Instead, what we do in those languages is supply bindings to the C++ library. So the situation in R is that when you install the Arrow package, what you're actually doing is you're getting two things at once. You're getting the Arrow R package, and you're also getting the C++ Arrow library. And this is a distinction we'll try to keep clear in our heads as we go along. The C++ engine is the thing that is kind of, I sometimes think of it as Arrow itself. It implements the Arrow standards. It has its own memory allocated to it. It has its own compute engine. The R Arrow package links out to it. And so it does a whole lot of the work on its own and makes sure that R plays nicely with this C++ library. So that's the distinction between the two, and we'd sometimes get a little bit sloppy when we talk, and we refer to both of those two things as Arrow, but they're two different things. And they both get supplied when you install the Arrow R package. Okay, so that Arrow is this project that attempts to span all these different languages so that all those languages can access this one common standard. Which kind of brings me to the second function of the Arrow project, which is accelerated data interchange. One of the big fundamental difficulties we have in a fragmented world is that we're constantly passing data around, right? There are many, many different applications, there are many data sets, and we are constantly sending data from one process to another. We're loading data in and out of memory, we're doing all sorts of things, and we're often sharing them between applications. Every single time we do that, we have a tendency to incur a serialization cost. So if I want to, for example, if I've got something I've written in an application I've written with R, and I want to send this over to a friend who's working with Python, and they've written their own code to that, sending a data frame in R to a Panda in Python is not a straightforward operation, where they're not the same underlying structure. You can't just say, oh, hey, Python, can you go and look at this bit of memory that's been allocated to R and pretend that that's a Panda? Like, that's not going to happen because they are fundamentally different structures. So in order for those things to communicate, if I need to serialize, so my data frame needs to be converted to a series of bytes. Those things have to be transferred over to Python. That needs to be then unpacked to convert it into memory and so on. Those serialization costs are hugely expensive. They take up a staggering amount of time, especially as your data sets get bigger. And once you start communicating data over very constrained channels, like you really don't want to be like large data over narrow channels. You really don't want to be, wasting time reorganizing your data. It would be a lot simpler if we had an agreed upon common standard that says this is how we will format a tabular data structure. Now, if we have this agreement that we say that tabular data structures should look like blah, I don't actually care right now what blah is. For the moment, we will, like eventually we may say that thing should be called arrow, but whatever. This thing has, as long as there's an agreement, it can be anything. Then you have the ability to say, well, hold on, R and Python both know this same data structure. So I don't need to reallocate stuff. They can just pass pointers around between one and the other. They don't actually have to send the whole freaking thing over. So you get to get rid of all those serialization costs. And it makes it much faster for things to be communicated from one to the other. And I'm going to pass this over to Jonathan, who's going to tell me I'm wrong.
No. I might have missed this in the power shenanigans that the hotel just experienced. But if you haven't explained, what is a pointer?
Oh, right. Right. Yes, I keep forgetting these sorts of things. I just so yes, pointers are basically, here is, okay, very quick computer sciencey thing for non-computer scientists. I am also a non-computer scientist. Big block of memory, got a bunch of stuff in it. And if I just want to say, hey, can I say, look, give me the location of this thing, this enormous chunk of thing in the computer's memory. The thing that tells you the location of the data in the computer's memory, that's your pointer. It's basically just saying it's a location of, and it's an address in memory, essentially. So instead of passing the whole data set around, you're just telling it the address. That's how I think of pointers. And when they show up, they're usually a big long string of numbers that you don't pay any attention to. Okay. All right. So hopefully that gives you a bit of a sense of the idea of why it's useful to have some sense of standardization. If all of these languages can agree to use a common standard, then we get a whole lot of efficiencies for free. Next comes this obvious question of why should we agree to your standard? Like if I'm being the jerk, as I often am, and saying, well, should anybody agree to say, well, why use Arrow rather than, Blarrow or whatever? I don't know. It's very early in the morning. It really is. If you're going to have a common standard, it should be a good standard. It should do something else well. So one thing that Arrow is designed to do well is efficient in-memory processing. This is the bit in that little haiku about in-memory analytics. So this is the idea. This has taken me ages to grasp. When we do data analysis, right, we are very typically operating on one or more tables. And a tabular data structure is this nice, it's this rectangular object. And it has a fundamental deep asymmetry to it. Rows and columns are not the same thing. Columns describe variables, rows describe cases. And the contents of these things have different kinds of relationships to each other. So I've tried to show that in this diagram with this color coding, right? So if I've got this little toy data set that I've just created here, which has some locations of some fairly famous riots, and the year that they took place in, and the city that they took place in. If you look at the data column-wise, right, so if I pick the year column, where's my, oh, there we go. Adjacent cells in the column are structurally similar to each other. So they are the same type of entity. So the year 1969 is an integer, as is 1966. Not only that, it refers to the same kind of entity, the same kind of semantic entity in the world. They're both a year. Similarly, location. Stonewall Inn is a physical place. It's a string in memory. Compton's Cafeteria, also a physical place. It's a string in memory. These things are similar to each other. If you go row-wise, you don't get the same similarity, right? Stonewall Inn is not particularly similar to 1969, and 1969 is not particularly similar to New York. And in truth, Stonewall Inn is not particularly similar to New York either. Like, even if you changed the rows, the columns around, those wouldn't be similar insofar as a city is a different thing to a bar, and the things you want, the questions you want to ask about a city will be different questions that you want to ask about a bar. And I realize that that's very philosophical, but it turns out to have actual practical implications. So here's the bit where we start looking at what those actually are. Let's suppose we're going to have to chuck this thing into the computer's memory. Now, computer memories don't have tables. Like, it's just a big, long, flat, sequence of addresses. And so that table has to be flattened and put into memory in some order or another. And we can either put it in row-wise or we can put it in column-wise. If we put it in row-wise, so we just read, we read it like it's a CSV file, right? So you just go left to right, then down a row, left to right, down a row, left to right, and so on. You get this buffer here, where you get this thing. If you do it the other way around, I can go, okay, we'll just grab the leftmost column and go down, then shift right, grab the middle column, go down, shift right. You get that shape. Now, I've color coded it to highlight the column similarities. Where this becomes super helpful is when we look at how modern CPUs are designed. When I'm going to go and do something like, say, a filter operation, so let's say I'm going to go and do a database operation, but in dplyr, this could be this would be a filter. I want to go, okay, well, pick the subset of cases, so find the rows in my table where the year was 1969. That's a super common operation whenever we're doing data analysis. That's basically, that's one of our bread and butter things. So we are constantly querying, we use the contents of a column to subset or to pick out particular, to pick out a subset of the table that we want to do other operations on. When we do that, there's a feature in sort of modern CPUs called single instruction multiple data that says, okay, well, what I can do at the CPU level is grab a chunk of adjacent blocks in memory and do the same low-level instruction on those. So you get big speed ups because you can do essentially the equivalent, like you can do a vectorized operation at that level. So you can think of it as being a little bit like, like what we in R would think of as vectorization, or you can think of it as a little bit like multi-threading, but this is all happening at a lower level in the hardware. So a lot of the design of Apache Arrow as a standard at a low level is designed to take advantage of fundamental features of modern hardware to speed up a bunch of things. And that's really about as much low level, like that's as much hardware as I intend to talk about for this entire workshop. So that is I'll quickly talk a bit about what the Arrow package itself does, and then we'll take a bit of a break. Okay, so the Arrow package now sorry, pausing. Okay, the Arrow package in R, as I said earlier on, bundles two things, right? So it comes along, it's an R package, it bundles on all of that fancy low-level Arrow stuff with it. And what it will let you do is, there are two core types of functionality that it provides. Like I'm trying to group together a lot of different things. I think of them as providing read-write functionality and data wrangling functionality. So here's what it can do in read-write terms. There's a lot of stuff on this slide. If you start with the middle column, you can read and write lots of different data formats. So yes, it can read CSV files. Okay, fine. Everything, so many different things in R can read CSV files, big deal. Parquet files, which we'll encounter later in the tutorial, are extremely useful things for large data sets, which are harder to read in R. Like there's not as far as I know, there's nothing else in R that reads Parquet files. Feather is another data format which is associated with Arrow, also handy with large data set, but reading and writing Parquet files is a big deal. So being able to read those things either from local storage or from an Amazon S3 bucket is a thing that you can do with Arrow. You can read it, you can read things into an Arrow data set, which is that load as needed on disk structure, or you can read things into Arrow memory as an Arrow table, or you can read things into R. Enable between chunks communications if needed. Do you want to handle that one, Jonathan? Oh, sorry, I now understand that. Brian's question, I think, is asking about windowing functions. I think that's so yeah, if you wanted to create like calculate a moving average, so the Arrow pack, so if you're doing dplyr operations and you need to use like lead and lag or something to do operations that are applied across a group of things. Currently in the Arrow C++ engine, that's not supported. That is coming soon, I believe. What you can do, and there's actually an example of this later in the tutorial, is take advantage of the communication. Like there's a trick. Whenever you need to do that, you can pass the Arrow table or data set over to DuckDB. And so DuckDB supports Arrow data structures, and it does currently have windowing functions. So the solution to that problem, whenever it happens, is usually to hand over control of the data set to DuckDB, compute the moving average in DuckDB, and then you can pull it back into your regular Arrow thing. I'll talk a little bit more about that later on. So the answer is sort of yes. Okay. So I realize that's a little bit of a digression from where I was at. Okay. So, cool. Yay. I was helpful. I try to be helpful. I really do. Okay. So, you can read, write lots of different data types from lots of different places, and you can read it into either Arrow tables, which are things stored in Arrow memory, data frames, which are things stored in R memory, or if it's a freaking enormous thing that isn't going to fit into anyone's memory, then you can read it as an Arrow data set, which doesn't actually read the whole thing, but it knows how to handle it. Okay. So that's one use of the Arrow package. The other use, and the one that we spend most time using it for as data analysts, is data wrangling. And so here's the whole trick. Sorry, early in the morning. Okay, so it's a dplyr trick. One of the cool things about the dplyr package is that by design, it separates the user-facing API, which is the grammar of data manipulation. So that's all of those functions like filter and select and left join. That is separated from the backend, which is the code that interprets and translates those calls into the thing that does the computation. So when you are using dplyr normally, you're in what I think of as like the left-hand column of this diagram. So you're using the API that's supplied natively by the dplyr package. You're using the backend that is supplied also by the dplyr package. And all of the data structures that are involved are being implemented in R. Everything is being done in R. Okay, a lot of the code is also in C and C++, but let's ignore that little technicality for now. Like that's the whole point. Like this is the usual R-based workflow with dplyr. All right, but because of the way dplyr has been written, like all of those, the major dplyr verbs are generic functions, and anyone can go and supply methods for them, right? So this is the trick that underpins the dbplyr package. So for like, if you wanted to connect to a database and analyze tables stored in a relational database using dplyr syntax, all you have to do is load the dbplyr package, and that has a mechanism for translating dplyr code into SQL queries. And those SQL queries then get passed down to the SQL database that will return some results that get translated back up and returned as an R data frame. So dbplyr, in the normal course of events, if you happen to be familiar with that kind of workflow, gives you a way of working with databases in dplyr syntax. What the Arrow package does is provide essentially the same trick again for Arrow tables. So this time around, instead of having an SQL database as the thing in the background, what you've got is an Arrow table that's being handled by the C++ library. And And what we have here is the Arrow R package, which provides an interface between the two, which allows you to intercept any calls that you, the user, make to a dplyr function, translate that into code that the Arrow's C++ library understands, execute that, and then return whatever results you want back to R. And so the idea is to make that as seamless as possible. So that's essentially what we've been doing previously. Like earlier, when we were doing dplyr analysis on the New York City taxi data, we were operating on this rightmost branch of this little figure. We couldn't possibly have been on the left because the data set was simply too big. Like if we were trying to do it in R would just explode because that's data that just doesn't fit in memory. What you can do, so this comes out, I'll kind of foreshadow something that will come up later, and this is actually tied to Brian's question moments ago, is if you have a relational database system that also understands Arrow, which, as it happens, DuckDB does, there is absolutely nothing stopping you from just flipping from the rightmost branch of this dplyr thing into the middle branch that just says, I will start analyzing my data in dplyr syntax and have it be interpreted by the Arrow package, and then go, oh, I'm hitting something that the Arrow package doesn't know how to translate. So I'll just flip over, pass it over to my relational database thing, and then continue with the analysis in there. Intuitively, that feels like it shouldn't work, right? Because to my mind, what I think every single time is, wait, am I picking up 2 billion rows of data and moving it from one backend to another? That's got to be insanely expensive, but it's not, right? That's the whole point of this standardization trick. If everybody understands what Arrow tables are, the only thing that ever has to be shared between the rightmost branch of this, the Arrow, what do I think of as the Arrowplyr branch on the right, and the dbplyr branch in the middle is just some metadata. Like it only has to pass a little bit of information back and forth, and everything can happen completely smoothly. So there's nothing stopping you flipping back and forth between the 3 different branches of this dplyr tree to get access to the bits of syntax that you need. And we'll see this a little bit in the workshop as we go, which I think is kind of cool. I think we are at time for a break. So should we take a 10-minute break for everybody's sanity? And in my case, I desperately need a coffee. Sound good? So we'll come back at, I guess at 2 hours and 5 minutes left on the clock. Yes? Okay. This is my fourth coffee for this morning. I don't normally drink this much, but it's terribly, terribly early. Okay, right. All right, let's get back to it. Hopefully everybody has used their 10 minutes wisely and is feeling slightly refreshed. All right, so I'm going to start talking about data wrangling in Arrow, and a lot of this is going to hopefully feel super familiar to you already because it's essentially just going to look like data analysis with dplyr. What I'm going to do as I go is try to pick out points, like potential pain points that you might encounter as you're doing data analysis with Arrow. And just talk you through some of the processes I've gone through in trying to debug my own Arrow pipelines. Okay, so let's put myself in. Okay, here we go. So as we've seen earlier in the workshop, we already have a very familiar syntax, right? So we've got, here's our NYC taxi data. We can filter, group, summarize, and mutate. And that all feels very normal to us because we're an R users, and this is a really common workflow for us. A thing that is super helpful to keep in mind is that the output here, if we don't collect it, is a query. This hasn't actually been evaluated yet. So all that this is really saying at this point in the process is we are prepared to execute something, but we haven't done it. A standard difference, and you see this in both dbplyr pipelines and in Arrow pipelines, you need to explicitly tell the dplyr pipe to execute. And in the case of Arrow, there are two different notions of what that means to make it execute. And it's sort of helpful to think about which one you want to do. The two options that you have are collect and compute. So compute will evaluate the query, and the output will stay in Arrow. So it will, anything that gets loaded will be loaded into Arrow, computations will be done locally with Arrow, and results will stay in Arrow as an Arrow table object. Nothing goes into R except for metadata and little bits and pieces. Collect, on the other hand, does all of the above, but then takes the final result and returns that to R. So if in most cases, when you are ready to finish off your data analysis, like usually you've got to the end of your pipeline, you're actually genuinely ready to pull something back into R because you've got a small thing, you probably want collect as the way to make your query execute, but not always. And it's worth at least highlighting that distinction so that you understand exactly what you're doing when you make your query run. I'm going to make sure that speaking of, hold on, just making my, yes, so if the result is larger than memory, collect will fail. and compute file. Yeah, I believe it does. I'm fairly sure that Arrow, alas, does not supply the magic that would allow the memory to be larger than memory. So
There
I
are
think
certain circumstances where the representation in Arrow would be smaller than R's memory representation. There is like a bit of window where you can load something in that would crash R, load something into Arrow that would crash R, but would not crash Arrow.
yes, that's a good point.
And we are actively working on kind of spilling to disk when those circumstances happen in the query engine, though that's not quite ready yet.
Oh, I didn't know that. Oh, cool. Okay, that would be neat. All right. So this is.
Oh, and actually, one more thing.
Yep.
If you are writing a data set to disk, Arrow is smart enough, and it'll tell the read to kind of back off if the read starts producing more data than can fit into memory. So if you're doing a read-write pipeline where you're like repartitioning or adding columns or something, Arrow will know when to kind of hold back and only read in as much as it can right out to the write buffer.
Oh, that's handy. Okay. I understood most of that too. All right. So, okay, so this is yeah, just so we could. On the slide here, you can just see the coin collect. This is exactly the same thing we did in the example earlier on. This is producing the exact same result. The only thing you're seeing different here is that I've timed the result. So it's taken me about 2 seconds on my laptop to do this computation on the data set. Sometimes it will be longer than that, sometimes it will be shorter than that, and so on. But I'll try to, as much as possible, show you the amount of time things take, as we go, just to give you a general sense of, how long things take. Okay, so here are some kind of examples of things that there are limitations to how much of the dplyr grammar is understood by Arrow. So, for example, one thing you can do, right, is if I want to mutate multiple columns, I can do that just fine. So let's say I want to express the, for some reason I've decided I want to count the number of trips and shared trips in the millions, right? So I've just written a little convenience function here that just divides everything by a million. And so I'm mutating my data so that I am, expressing both trips and all trips by in the millions. That works fine, right? Mutate, perhaps not surprisingly, can handle mutating multiple columns. If you're doing this in dplyr natively and you're starting to thinking about wanting to do the exact same operation on multiple columns, you start thinking, okay, well, maybe there are other ways I can do this, right? And I'm like, so up until quite recently, the natural way to do this in dplyr might have been to use one of the scoped verbs, right? So I might try to do something like mutate at. And so I could just say, well, for these two variables in my data frame, or in my data set, sorry, can you apply the millions function? That won't work in Arrow currently, so Arrow doesn't understand the scoped verbs. And similarly, if you want to use the more recent across-based workflow, you can't do that either. So that's not a thing that's currently understood in Arrow. So if I wanted to just say, well, grab the variables that end with trips, apply the millions function to those, I can't do that. Arrow in the select function does understand tidy select specifications. So it does understand the ends with function, but it doesn't know how to interpret across. Like our problem here is the across function that's giving us some difficulties. Now, often that does mean that you are stuck with having to write queries, writing things manually where you just have lots of things. And yes, as Jonathan's pointing out, we do plan on adding those things. Like it's not like unaware of this. It's going to happen, but you should nevertheless be aware that this is a current limitation. And of course, one solution to the problem that you can actually surprisingly often get away with is you can collect first and then do your across thing. So this obviously will not work for every pipeline, but it's surprisingly common that I've found in my own analyses that I can get away with doing really simple things. Like I just do the, so just do so going back over here, there we go. So here's all of the computationally expensive stuff that has to be done in Arrow, right? And in particular, the part that's difficult here is the group by year and summarizing, right? That part there is where I'm really stuck dealing with an extremely large table, and I can't do it in anything other than Arrow. That part of the pipeline I can't do natively in R, but subsequent operations, once I've shrunk, once the table's been shrunk down, there's nothing stopping me pulling it back into R and continuing the rest of my analysis using regular dplyr syntax. And I mentioned that basically for the reason that, like it's not a cop-out. So there's a part of me that feels like, whenever I'm writing my own analysis things, I feel like I'm almost cheating, where at the end, if I just go, oh, well, I'll just collect, I'll pull this small table into R, and then I'll do, whatever little thing, whatever fancy cleanup stuff I need to do in R. But that's kind of the point, right? You can do the expensive stuff with Arrow, and then you can add whatever syntactic, whatever fancy sugar you like with R. This is a perfectly legitimate way of dealing with things. All right. Let's talk about other types of operations that are understood in Arrow. So Arrow doesn't just understand dplyr things. So a fundamental thing in understanding both the dbplyr arm of that diagram and the Arrow diagram is that there's two different types of translation that goes on whenever you're creating a dplyr backend, if you're ever doing this yourself. You have two jobs. You've got to translate the dplyr verbs themselves. So you would have to write code to understand what a filter operation is. But you also have to translate the code, the expressions that go inside those dplyr operations. So you need to be able to understand those things, right? So that's a little bit like saying, yes, I do need to understand what a sum is. I do need to understand what a cross is. And apparently we don't currently have that. We do need to understand all sorts of things. So what operations are supported and not supported is basically a function of what we've had time to write support for. But there's an understanding that that's not just dplyr. And a big thing that we're often doing in our regular data analysis is things like text manipulation, and that means stringer for those of us who are working in tidyverse. So if you are following along at home and wanting to do this yourself, there's an ancillary data set that comes along with the New York Taxi data, which gives some meaning to these zones. So if you remember when I said at the beginning, when people are being picked up from some location in New York City, the data set records the pickup location with this numeric code. So it will say, well, I've been picked up in yeah, so I've been picked up in zone 5. That doesn't help very much in telling me things. It does help a little bit more to know, you know, I've been picked up in Arden Heights, whatever, you know, that, whatever that is. I do know where Staten Island is, at least, you know. So this little table at least is useful for interpreting the taxi zones. Importantly, for current purposes, it's got some text in it. So I'm just going to quickly, so here we're loading this as a data frame. I could alternatively, I've taken the same thing, use the arrow table function to convert it. We'll just represent this in arrow as a table. And so this is now in arrow memory as a table, and I can now do some string operations on it. It's worth unpacking this just a tiny bit before I go on to do the string manipulation stuff, because I find myself thinking a lot of the time trying to track where things are going. So we had a CSV file on disk. We've used read CSV arrow. It appeared in our memory as a data frame. I cleaned up the names of it, and then I imported it into Arrow as a table. That's not necessarily the optimal way of doing it. There's an exercise in the tutorial in trying to go straight from the disk to Arrow memory if you want to try that, but I'm not going to cover it in the tutorial, like in this workshop right now. What I do want to mention right now, sorry, is that the thing that we've just loaded, or the thing we have in R here in this New York City taxi zones arrow table, does have a, you know, has a dollar method, so we can inspect the columns of it, and has a print. When we prints out, it looks somewhat similar. Like you can see, it's printing out something that looks like a vector. The thing it's printing out here is called a chunked array, and there's an immediate sense of wanting to go, why is it chunked? We'll talk about that later on in the workshop. This was one of those things that tripped me up earlier on. I'm kind of going, arrays, okay, I can assume an array is something like an R vector, and it sort of is, but what does it mean to say that this thing has been chunked? This is a slightly more complicated story. We'll get to that one momentarily, but I'm calling attention to it because you will encounter this. Okay, let's get on to string manipulation. I'm not going to ask you to do a lot of stuff because we're going to run short on time. So instead of doing that, I'm going to give you like 60 seconds just to think about this table and go, okay, how would I process this in R? So specifically, let's go, all right, I want to remove all the vowels from the name of the zone and all the text that follows the slash. I want to, once I've created an abbreviated string using that, I want to count the length of the string, and then I want to take the resulting table and arrange it by descending string lengths, right? And so the answer would be, so the question here is, how would we do this, right? So here, just to, if we've got this data set, how would we abbreviate this, calculate the length of the abbreviated field, and then sort the results? Hopefully everyone's had time now, not necessarily to solve it. I suspect many already have, but at least thought through what commands you'd want to use. Let's have a look now at how I did the same, how I solved this with the doing this with Arrow. So what I've done here is taken the New York City taxi zones Arrow. So this is the object that's in Arrow. That's that Arrow table, and I've mutated it. I've created the abbreviated zone field. So I've taken the zone variable. I've piped it to still replace all, right? And I've got my little regular expression here that matches a vowel, matches the vowels and apparently also apostrophes and space, replaces those with an empty string. And again, another string replace operation that grabs everything after the slash and replaces that with an empty string. I then take the results of that and I pass to another mutate statement, and I grab the abbreviated zone and I just use stir length to calculate the length of the abbreviated string. And then I do my select just to grab the fields that I actually care about, and arrange things in descending order of string lengths. Okay, this is probably pretty similar to the solution that you would have come up with, but I'm guessing, well, I'm hoping that it's at least similar to, sorry, I'm just gonna get my sound back. There we go. But if you've been doing this with tidyverse, you know, with Stringer, there are some questionable, or what feel like some questionable choices I've made. Like, one obvious one is, why on earth have I broken my mutate in two? Yes, you can always do G sub and B apply. So the mutate, like normally if I was doing this in R, I wouldn't split this over two mutates, right? Like I could create the abbreviated zone like variable in the first argument to mutate, but then there's nothing stopping me calling that newly created variable in the second argument to mutate. Like the whole point of a lot of, you know, one of the nice little conveniences in mutate is that it will evaluate sequentially so that you don't have to break things in half. The implementation of mutate currently in Arrow doesn't let you do that, so you actually have to split it into these two separate things, because if you try to put this argument inside this call to mutate, it will throw an error and complain that the ABRZone variable doesn't exist. And that's a subtle difference between the Arrow implementation of mutate and the native dplyr one. It's not intended, like I don't believe that's a design choice. I think it's just an, you know, that was a trickier thing to implement. Another difference that you'll notice is why have I, or another questionable choice here is, why did I use stir replace all rather than stir remove all? Like in truth, if I'd just gone, look, why don't I just remove all the vowels? Like this, replacing it with an empty string is really not necessary, because Stringer has this little convenience function that would allow just remove things. Like it's just a wrapper that replaces with an empty string, but you know, it's very convenient. As it happens, there's no binding for that yet in the Arrow dplyr, so you can't call it right now. It wouldn't be hard to add. I imagine it's going to appear very soon. These things have a tendency to vanish like about a week after I find them. The rate at which Arrow seems to be under development means that every single time I point out that we're missing an obvious binding that should exist somewhere, you know, somebody immediately creates a pull request and then this absent vanishes. So I'm sure that someone's going to fix this one immediately. But I discovered this the other day, that right now there is like the Arrow plier, the Arrow dplyr backend does not understand what stir remove all is. So it doesn't understand stir remove, so you have to treat it as a stir replace, which is irritating, but not that irritating. Like, it's easy enough to fix. So you will encounter minor irritations like that as you go. And one thing that I found early on is to realize this isn't me. This is often, you know, it's just that there are these missing bits of functionality because there's lots of functionality to add. Okay, so anyway, once you do it, you get this as a result and everything looks great. I'm not going to bother to reproduce it. You can do it yourself whenever you like. Like, all this stuff is in the tutorial. Like, I sort of want to try and make sure that you get to see all these stuff now. There's exercises available. You can go and click on this. You can practice these things if you feel like it. Excellent question from Maria. If you, what if you define stir remove all in your code? Would Arrow understand it? So yes, no. You can write functions that will be understood by arrows. So you can write if your stir remove all function, I think, is comprised entirely of binding of functions that Arrow already understands, I think it can execute it fine without causing any problems. You can also, there are also ways of writing fancier low-level bindings. So if you really, really wanted to, you can do all sorts of, you can write your own functions that will behave, that you could just chuck natively into the pipe. When, does somebody else want to take a go at giving a better explanation than that? That was actually really bad on my part. I'm not happy with that answer. The answer is yes, I think you can.
Yes, yeah. So like Danielle was saying, you can register a binding, and this uses kind of the underlying functionality that we do to write all of these. We can't yet do the situation where you have a function that is comprised of all things that are known Arrow functions already, but someone is actually working on that. So hopefully that will happen very soon, because it should just work. And it's actually like a silly namespace issue. It's not actually an execution issue. But so not yet, but soon.
Thank you. I wasn't quite sure where we were on that one. Awesome. This is why this is why we have Jonathan around. Also, they're lovely. Okay. Right. So along the similar lines, there's a lot of so support for lubridate functions is coming online. So I'm not going to talk too much about it right now, other than to mention that so date time functionality is something that didn't exist until quite recently. It is now quite rapidly appearing. So some parts of the lubridate package, so some functions in it you can now do. So here's an example of things you now can do. So if I wanted to grab all the pickups that in January 2022 that occurred at pi time, so the hour is 3, the minute is 14, the second is 15. Yeah, I know, I'm being silly. I can do that because I can use the day, hour, minute, and second extractor functions that are supplied by the lubridate package. So Arrow understands those. And you can also understand things like W day. So if you wanted to get the name of the weekday or whatever, it will pull that out. So there's a lot of that kind of date time functionality that you can take advantage of. And when you do that, you can get, so if I wanted to compute that, I will get a result that says, okay, cool. Here is a timestamp. I'm calling compute for a reason, because I'm going to call attention to something in 2 seconds time. But really, I can't read this compute thing, so let's do it again with collect this time. And I go, yay, okay, so there were exactly 5 pickups in January 2022 that occurred at pi time. Except if you look at the results, I'm guessing your first thought is going, why are they all saying 14, 14, 15? Your first thought there is this a bug in Arrow? And the answer is no, this is a bug in time zones. Time zones are horrible. So this is an Arrow R. This is a slight communication difficulty that pops up whenever time zones are involved. What's happening here is, internally, I told you this was relevant, we have a timestamp object in Arrow, which has recorded the time in UTC. And when I specified in my query hour equals 3, or actually, I suppose, when it's extracting the hour on the pickup date time thing, it's extracting it from that UTC date time. That's a perfectly legitimate thing to do, but I might want to do it in some other time zone or whatever. But I haven't done anything fancy to it, so all it did was just use the native encoding, which was UTC. So great, that's fine, but then why on earth, if all that stuff was being done in UTC, why am I getting these 1414s at the end of it? And the answer is, I'm in Sydney. And R has a funny opinion about dates and times, where it says that if you have a date time object, in particular, if you've got a POSIX CT time that doesn't have a time zone attached to it, it will print it out by substituting your local time zone. So this is which for me is UTC plus 11. So we're getting that 14 because my time zone is 11 hours ahead of the time zone in which the query was done. Yes, that's annoying. I hate it. This is some weirdness with the weirdness is coming from the R print method for POSIX CT objects. That's not, so it's not like, this is not a problem with Arrow per se, but it is a pain. And managing time zones in general is still a little awkward. That's a thing that is under active development, but time zones just in general are painful. Anyway, you will, if you're doing date time stuff, you will run into that one, and when you do, that's the reason why. There's a bunch of other functionality in there that you'll find that currently doesn't exist but will soon. So for example, currently you can't do rounding with date time objects. But the only reason for that is that I haven't finished writing the pull request to make that happen. So it will happen very soon. Really, it will, I promise. So that's date time stuff. Database joins. I mean, it is rare in life that we are operating solely with a single table. It's nice when we can, because I like it when everything is all in one nice, neat little package, but that tends not to happen. So Arrow now, I think I'm trying to remember if it came out in Arrow 7 or Arrow 8. I think it was 7. I don't remember. Anyway, yeah, Arrow 7. Now will support database joins. So it understands things like left join, inner join, and all of that kind of stuff. All those sorts of dplyr functions for handling merging of tables. And I'll give 2 examples of that here. And the first one, everything's going to work smoothly. It'll be a little toy example that you don't need big data stuff for. And everything's going to go great. And then the second example, I'm going to do it with the real data, with the New York City data. And then things are going to break. And I'm going to show you why it breaks and then fix it. Because, again, this is a thing that happens in the wild. Okay. So we're going to use Palmer Penguins data, which I imagine many of you will know. It's not, it actually doesn't matter what the data are for our purposes, but they're penguins. They go around doing things on islands, being penguiny. I don't know. They're cute. That's good enough for my purposes. All I care about for now is that they're on these Antarctic islands, and there are 3 islands in the data set. Torgerson, something or other that starts with a B, and Dream. And the data set, for some reason, doesn't tell me where those islands are. That's obnoxious. So for some, later on, I might want to plot geographic stuff. So it's entirely possible that I might have an auxiliary table, which, you know, for reasons known only to me at 3 a.m. when I decided to write these slides, I have entered directly as an arrow table. So I've just gone location gets arrow table. So we've got, I have defined an arrow table using syntax that looks very similar to the way you would define a data frame or a tibble. So island equals Torgerson, Bisco, Dream. Here's our longitudes, here's our latitudes, and so on. And here's our entirely unhelpful print method. There are reasons it does that, but anyway. So we have our little ancillary table. And so what I would like to do, right, is a left join. So I've got, on my left table here, I've got the original penguins data that's got 300 and something or other rows. And here are a few of those rows. So here's different species, the islands on which that particular penguin was observed. Here's some other variable. And I want to join on island conveniently. They've got the same name, so I don't have to do any ugliness with telling it which variables to match on. It'll just automatically join on the columns that have the same name. And I want it just to insert longitude and latitude, right? So I'm going to get an output table that looks like this. So we add in, here's our longitude column, here's our latitude column. This is our left join that we are super familiar with. Okay, let's go and do that. The syntax for this is exactly the same as it is in regular dplyr, just with a collect chucked at the end, right? So we've got penguins. I've converted it. So I've taken the penguins tape data frame, converted it on the fly into an arrow table. I'm left joining it onto the location, the table that I just created, and then I'm just selecting the columns that I care about and collect to execute the query. Right? So that gives me the same. So it's got one row for every row in the original penguins data, but it's added these 2 additional columns. So we've got the longitude and latitude columns. So that's our left join. Everything works beautifully. So why am I bothering to tell you about it? Because in the wild, fun things happen. All right, so here's another example that has the exact same structure, but we're now using the New York City taxi data, and we're going to use the two tables we've seen so far. So our main table, the left table, is going to be the original NYC taxi data. That's the thing with 2 billion rows in it. It's got all those ugly numeric codes in it. And our right table is going to be a slightly modified version of the taxi zones ancillary table. The only difference is I'm just going to rename columns so that, you know, we have it, rename the columns so it will just automatically join on pickup location ID, right? So we're going to have it say, okay, can you please just tell me, like, all I want to do, not trying to do anything complicated here, is just insert a column into my table that says what borough in New York City did the pickup occur in? Was it in Queens, Bronx, Manhattan, whatever, right? Or EWR, which is not actually a borough, that's in New Jersey, that's Newark Airport. I know all sorts of weird things about New York that I didn't know before. Yay. Okay, so that's what I want to do. Just adding this column that says what borough was the pickup in. So that seems like I should be able to do this really easily. All right, so here we do. Let's just reorganize so here's my New York City taxi zones table. So that's the one that has the coding for the zones, right? And all I'm going to do is I'm using my select function here to simultaneously reduce it to two columns, and give them the names that I want. So I'm just going to have the pickup location ID, pickup borough. Okay, so this is going to be my right table in this example. Okay, so here we go. So we go New York City taxi, and then all we have to do is just left join onto pickup, and we collect, and this should work, right? Because we'll go back to this. In our original table, this should be NYC taxi. It does have a column that looks exactly like this with pickup location ID, and it has these integer values. And the right table also has these integer values for pickup location ID. This should automatically join on that column, right? And it should then join on that. It should insert the pickup borough column. And why on earth is this whining at me? So if we unpack this error, we look at incompatible data types for blah, 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 blah. Yes, this is how I read error messages. Pickup location ID of type int64 and blah, 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 blah of type int32. Okay, this happens occasionally, and I hate it. So what's gone wrong? The problem that we have here is type mismatch. So in the New York City taxi table, so the big one, the pickup location ID has been encoded as a 64-bit integer, right? And we can check this by inspecting the schema. So every data set, and in fact, Arrow dataset table has the schema method. So if I just go NYC taxi $schema, it will just print out some basic information about the names of all the variables and what type of object they are. So the vendor name is a string, blah, 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 blah. Let's go all the way down to the bottom where the piece of information we care about is hidden. Pickup location ID is int64, all right? So that is a 64-bit integer. Yay. All right, now, Um, excellent question. Yes, this does not need to be a 64-bit integer. This is a number that could only go as high as 265, so we probably don't need to allocate 64 bits for it. But we have, and I'm not going to recast. I'm not planning on casting it, so it's there. Okay. It also makes a good example, so I'm sticking with it. All right. So the thing is, Arrow, because Arrow inherits a lot of stuff from C++, right? It has all of the different integer types that C++ has. R, on the other hand, is like, I don't need to have 8 different types of integer. We can just have integers, please. So R integers are natively 32-bit integers. So when I take the pickup table, which I had carefully chosen, so I had very carefully just loaded into R, not thought very much about its structure, converted it to an arrow table. When I have a look at the schema of that object, the location ID, because that was an R integer originally, when it gets ported over to Arrow, it shows up as a 32-bit integer. And so because of that, that counts as a type mismatch. And Arrow refuses to join on things of different types. So it's pretty strict about stuff like that. So to fix that, what we have to do is explicitly take control of the schema. So generally, it's easier to do this, as much as possible. You probably want to do this with your ancillary tables, like stuff around with the little table, not the big table. So here's what we're going to do. We'll take our New York City taxi zones table, like that's our table in R. And when I go to convert it to an arrow table, I'm going to specify the schema argument to the arrow table as arrow table function. There's a schema function in the arrow package, and what that takes as input is a list of, so you just give it variable names, so like location ID, borough, zone, service zone, and so on. So these are the variables that are going to end up in your data set. These are the variable names. And over here, you've got functions corresponding to each of the data types. So if I want location ID to be ported over as a 64-bit integer rather than a 32-bit integer, I need this line. Like this is the one that's going to solve my problem. By default, that's going to show up as a 32-bit integer. My children are waking up, so I'm waving at them. The strings are the character vectors. UTF-8 is the name of the data type for strings. So those are just the default values, and that's not making that's not affecting anything that matters here. The thing that's going to solve our problem is making sure that we end up with a 64-bit integer and not a 32-bit integer. Okay, there's a whole bunch of these different type functions in the arrow package. Like if you go and look at the help function, like the help documentation, you discover there's things like Boolean, that's logical, date 32, there's timestamp, there's a whole bunch of them. I'm not going to try to exhaustively list them, but that gives you a sense of it. Okay. When we do that, you can see that what comes through is, yep, we end up with we have the schema that tells us, yes, this is 64-bit integer. And that's going to fix our join. So here's what I'm going to do. Let's do the same thing. I'm going to, so again, take our New York City taxi zones, which has now been ported into Arrow in a format that is not going to cause type mismatch. So I'll create 2 auxiliary tables, one for the pickup zone and another one for the drop-up zone. They're not like, they're obviously doing the exact same thing. They're just keeping the location ID and recording the burrow. So we're going to join on both of those 2 things. So we'll add a column for the pickup burrow, another column for the drop-off burrow. So we're going to join on both of those 2 tables. And then we're going to, because I need to do something with my join, like, I'm going to cross-tabulate. So I'm just going to count the number of taxi rides that start in one pickup burrow and end in the other pickup burrow. So we'll cross-tabulate and pick up and drop off burrow, and then I'm just going to arrange them. To answer There's a question there about, is it possible to modify the schema without specifying all the rest? I don't think you currently can. I think I've tried that and it throws an error. I'm not sure why. That doesn't seem like a required design choice. Like, it seems to me like you should just be able to specify some and all the others would come through with their default values. But at the moment, when I've tried that, it throws an error. So I think you have to give it an exact schema currently. Okay. So anyway, if I do this with the full 2 billion row data set, that takes about 8 or 9 minutes or so to complete on my laptop. So, that's one I'm not going to do ever in live coding, but that's still, not terrible performance, I feel. Anyway, I feel like I'm starting to get a bit blasé about, oh yeah, just billions of rows and cross-tabulating and joining them. And I'm still getting used to this whole I do big data stuff now. Okay, here are our results. So you can see we have, in most cases, the burrows, just like the location ID was still missing, but we've got data for enough of them that we can see that for most of the data are just taxi rides within Manhattan. Like, that's easily the biggest subset of the data. I have a suspicion that has a lot to do with where the data are coming from, like who's providing the data rather than anything else. But I actually don't know that much about the data set. Really, the whole point of that was to highlight the fact that when you're doing joins, so when you're doing 2 table stuff, you have to care a lot more about your data types, because your chances of running into a type mismatch problem are much higher. So that was the reason for bringing it up there. Okay, there's an exercise you can do later. I don't think I'm going to torture people with that right now, because there are other things I want to talk about. Do we want to go for another break? I feel like I've been talking for a while. Does it seem like break time? Yes? Okay. You do 10 minutes for the sake of everyone's sanity. So if we come back with an hour left on that clock, although I guess that clock runs later than the scheduled finish time. I don't know. I'm very confused. All right, I'll be back about 10 minutes. And we're back. Or at least in theory, yes, we are back. Okay. So it looks like on the schedule it says we have the full hour of what's left. What I think I'm going to aim to do is wrap things up in less time than that, so that we've got time left for questions or just giving people breaks and so on. So I'll aim for about another half hour, but probably a little bit longer, and that'll give you time to ask any other questions you might have. Okay, so I promised earlier on an example where you can use DuckDB together with Arrow. And this is a really nice example where you've got something that is actually a relational database system, like it's an SQL database, that plays nicely with the Arrow package just because of the fact that both of them understand the Arrow specification. So here's the problem that we're going to try and solve. And it's sort of one that you wouldn't think intuitively would be a problem, but actually sort of is. So if I go, let's take the penguins data, convert it to an arrow table. I then try to add the row number as an ID column. And then I want to go and do some other things with it. And it doesn't actually matter what the other things are, because our problem here is with this bit. I am calling row number. Row number is a window function because it requires me to, the results of the computation on one row depend on other rows in the data frame. Arrow currently does not support window functions. So the Arrow computation engine doesn't. It's going to. It's not like this is a thing that's been forgotten. It's just a work in progress. And it's a bit of a pain because this is a sort of thing that you need to do, not that uncommonly. Adding a row numbers is a trivial operation that you might think of, but also just like if you've got sequentially ordered things, like you might need to do lag or lead type operations. Like there are all kinds of data analysis operations that will often require you to work with window functions. So that's an issue. Fortunately, the Arrow package is not the only thing in this world that supports the Arrow specification. DuckDB supports it as well. So there is a function in the Arrow package called toDuckDB that just seamlessly manages the handover for you. So early on, when I had this picture of showing you all of these different processes that could pass data around between them, there's still obviously some process by which, some mechanism by which they actually have to communicate with each other. The toDuckDB function handles that part for you. It provides all of the overhead or the setup to take this Arrow table this table that's in Arrow memory and say, hey, let's register this as a table for with DuckDB, and then that can be subsequent commands can be interpreted by that backend. So when we do that and just basically go through the same process, you get a result that is similar to what you'd get in dplyr. Normally not exactly identical, but now you've got something that's showing like this is the result of the query, but it's got stuff here that's saying, okay, the source is lazy query, database is, here we go, this is being handled by DuckDB. What's happened? I'm going to find. I did not. That was silly of me. I missed this. I didn't include a slide that I wanted to. Basically, what I have. Hold on. I remember. It's in the tutorial. I'll go over here to data wrangling at the very end. Just skim down to. Aha! This is the bit that I wanted to show. What's happening here when I use the toDuckDB function? I've just gone, okay, instead of using this arm of the dplyr diagram, just pass it over here, and now dbplyr is the package that's going to be handling the interpretation of the dplyr syntax, and DuckDB is going to handle the back end. You can use the toArrow function to pull it back the other way. So you can seamlessly flip back and forth between these two things, which is super handy. Anytime you've got something that's understood by one of them and not by the other, there is essentially no cost to switching back and forth because you're not really moving data around. So this is a very handy way of solving all sorts of problems that pop up like that. Okay, now, where was I? There we go. Let's go back to my slides. I knew there was a reason I had this written tutorial. Okay, so I can go and do something really similar like that. This is a silly example I came up with. Used the New York City taxi data, right? And so this is what I worked through on the website. I won't go through all the details. You can go do it yourself. But the idea was something like, okay, let's get the data from January 2022. I'm going to rank all of the taxi rides in chronological order by their pickup time. Apparently, I'm doing data analysis for a numerologist here who's really fascinated by weird superficial properties of the numbers. So we need to rank them by their exact chronology. We then need to find the taxi rides that occurred on where the pickup occurred on the 59th minute of the hour and the 59th second of the minute. And then the numerical rank of that ride has to contain the number 59 in it. And we want to return that rank. And we also have to extract this magic number that removes all the digits from the rank that are not 5 or 9. So apparently this is somebody who's really obsessed with the numbers 5 or 9, right? I realized it's a weird data analysis task. I was getting tired. I just wanted to pick something that would let me play around with these silly things. So here's how I would do this, right? I've got a problem here where I need to use window functions. So I'm just going to say, okay, I'm going to make DuckDB do all of the work for me. So I've opened a data set. So it's just a smaller version of the data set here. So it's just got 1 month's worth of data. So that's this bit over here. So I pass that over to DuckDB. I'm using window order rather than arrange. So if you want to know more about that, this is in the help documentation to dbplyr, but it's there to make sure that the arrange actually happens. But essentially, this is just arrange. So we're arranging the data by pickup date time, attaching a row number to it, and then I'm going to grab my trip ID, find those that contain the substring. So I'm going to convert them to a character, substring 59, find those that have a pickup second of 59, pickup minute of 59, do some string manipulation on that so that I can remove any digits that are not 5 or 9, convert back to an integer, select the columns that I actually want to retain, collect it, and all of that happens in about half a second. Okay, and here's my result. Now, I don't know why I'm doing stats consulting for a numerologist, but as long as they're paying me, I don't care. And I've got the result that I'm looking for here, right? So I've got my little magic number here for the rides. These are all we've got the pickup times that meet the criterion specified. The trip ID satisfies the criteria required, and so on. This is something I couldn't have done in Arrow alone, but thanks to DuckDB, which plays very nicely with Arrow, I can do this quite smoothly. And this is one of those things that kind of is the real advantage to having standardization. Like, it's really easy to do this kind of flipping between systems. Okay. So the last main topic I want to talk about is big data file formats. And so really I want to talk about Parquet files. I'm going to talk first about Parquet files, and then I'm going to talk a little bit about multi-file data sets. So the big data set that we've talked about, this New York City taxi data set, is split across 150 Parquet files. And some people will know what Parquet files are, other people won't. I didn't know about them until starting this job like 5 months ago. So I'm going to assume that you don't know, and I'm going to explain a little bit about why they tend to pop up when managing large data sets. Okay, so this part of the workshop is sort of focused on this sort of idea. Like, we've got Parquet files, and we're thinking about using them as a tool for big data sets. We're often, okay. Let's imagine for a second we're going to write a table to a file, right? And we're often used to secretly imagining a CSV file, right? Like, we imagine this thing that is written left to right, row-wise, and we write it so that when it shows up in our text editor, it looks vaguely like the table itself. Parquet files are not written like that. They're written in a way that's actually supposed to be helpful for the machines to read and index faster. So here's how it works. Imagine you've got this table, right? So I've got my same little teeny tiny table that I had before. This is my riots table. The first thing I want to do is say, okay, look, I'm going to have a lot of data. So I'm going to break it up into chunks. So we have chunks of rows. So we'll split it up, and I've only got 6 rows in my little toy example, so I'll break it up into 2 row chunks, like that. And so each one of them is now separate. For each of those chunks, we arrange the data column-wise. So a little bit like Arrow does in memory, Parquet does the same thing to it. Like, eventually, if you're going to write something to a file, it has to be flattened, right? So you've got to have a sequence of things written. So for each of those chunks, we arrange things column-wise. And for each of those column things, it gets broken up into these pages. The reason for organizing it like that, so here's this gives you an organization to a Parquet file that looks like this, right? So if you're reading the file from top to bottom, right? I mean, if it were encoded in plain text, which it isn't, you would open it up, and after some header stuff that we're not super interested in right now, you would see, okay, here's chunk 1, column 1, page 1, and it would just continue down like that. The reason for organizing things kind of like that is that each of these units of organizations is associated with metadata, and then at the end of the Parquet file is a whole bunch of extra metadata, which the Parquet reader, which it's not like we're writing a Parquet reader of our own, but the important point is that someone has. The Parquet reader can just skip to the end, look at the metadata and go, oh, okay, hold on. So chunk 1 contains rows 1 to 370. And I've got a query apparently that only needs rows 7. Okay, cool. I don't even need to bother reading the entire file. The Parquet reader can go and read the relevant bit of the file. The point of this is so the Parquet file is designed to have metadata that assists the reader. So that, unlike a CSV file, where it's pretty hard to avoid reading the entire file, Parquet files are designed to have a whole lot of additional information that makes them easier to only partially read. And you'll see some examples of that in the code later. So because of that, on top of that, they're also binary encoded and compressed, so the file sizes end up being smaller. But the consequences of all this is that relative to something like a CSV, a Parquet file is much smaller and it's faster to read and write. Like it's kind of the only advantage that a CSV file, for example, would have over a Parquet file is that it's human readable. In terms of the actual performance of the file for anything you might care about, Parquet files tend to do an awful lot better. Okay, so how do you, that's nice and all, but how do I actually do this stuff in R? Okay, so here is, turns out it's relatively easy in the Arrow package. So here's the path to a Parquet file that I have stored on my computer. So this is datasets, NYC taxi, blah, 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 blah. .parquet, that's the standard file extension. And the function that you need is just called read Parquet. And so in this case, if I go and read one of the Parquet files, so this is one of the 158 Parquet files that comprise the complete NYC taxi data. That's about 7 million rows of data. That's big, well, 6.5. It'll fit as a tibble. I can read it into R, and everything works nicely. Convenient things, though, about Parquet files, as I mentioned, because they've got this structure, right, you don't have to read the whole file. For example, you can explicitly say, I don't want to read all the columns. Because everything's been organized in this column-wise fashion, you can just read the columns you care about. And so there's a col select argument that just says pick the ones that you want. So I can read the Parquet file with columns whose names match pickup, right? That's a tidy select thing. So this will now return a tibble that only has 4 columns. So we've got pickup date, time, longitude, latitude, and location ID. And as you would hope, this makes a difference to your read times. So if you want to read the whole file, it takes about half a second. If you're only reading the columns you care about, so 4 columns, that cuts it down to about a quarter of the time. So you wouldn't get a corresponding speed up for CSV files because CSVs don't let you do that. There are some exercises. So later on, when you're working through the rest of the tutorial, so if you feel so inclined, you can play around with this and actually compare your read-write times for different things. There is a write Parquet file that it has the same structure as the read Parquet file. Functions. Sorry, I'm getting tired. It's handy. Okay, that's about all I really wanted to say about Parquet files. The thing that is maybe of most, I found most exciting is like once I understood the basics of reading and writing Parquet files and what they are, is thinking about, okay, if I have one Parquet file and it's got all this metadata that makes it easy to index, right? Because it's designed in a way that it can be only partly read, it makes it possible to create these multi-file data sets, right? I mean, this is what the NYC taxi data set is. It's lots of these Parquet files that all contain one small part of the New York City taxi data. So what we would like to have is an API or some way of working with many Parquet files and treating them like they're one data set. That's what we're going to talk about now. So if we have a look at the NYC taxi object that I loaded earlier, you see that similar to it having like a schema field, it's also got a files field. So if I just printed NYC $files, it will print out the path to every single file that's been indexed by the reader. So these are all 158 files. They all have a common schema. It knows how to find them and so on. What I wanted, sorry, I knew there was a reason I had this slide in. The thing you should pay attention to with this is noticing the file names. Here, so notice we have something that says, okay, NYC taxi, that's the name of the data set. We've got a subfolder, year equals 2009, subfolder, month equals 10. You will be entirely unshocked to discover that the part0.parquet file in that folder contains the data for month 10 of year 2009. I know, amazing, but this particular way of organizing the file names is called Hive partitioning. The name comes from the Apache Hive project, which I know literally nothing about, other than it had something to do with Hadoop. That's literally everything I know. The only reason I even bother to mention the name is that when you go and read the Apache Arrow, when you go and read the documentation, it keeps referring to Hive partitioning, and it gets a little bit confusing initially, like, what the hell is Hive partitioning? It doesn't mean anything particularly important other than it's this idea of, let's have the folder name be, this is the name of a variable in the data set equals value. So it's just, the folder literally has a name equals value pairing. And those folder names actually correspond to what's going on in the data set. When it's partitioned like that, the operating system can do a lot of the work for you, right? Because the file name tells you exactly where you have to look. You don't even have to look anywhere else. You can just go, the operating system says, oh, okay, we'll go open the September data, please, or whatever. So that will save you a lot of search time if your query is only relevant to a partitioned variable. So if you're only doing something that relates to the 2009 data, the only files I need to care about are these ones. I can load those and I can ignore all of those. So obviously that's going to speed things up. And so then we've got some examples here that are going to show exactly that. So let's do a filtering operation and we'll just count rows. Really boring operation. So take New York City data, go year equals 2016, month equals 9. So these are both partitioned variables, right? So in the NYC data, like when we look back at all those file names, year and month were variables that were used to help carve up those 2 billion rows in the first place. Because of that, this is a query that can automatically be restricted to, well, one file. This is exactly one Parquet file, right? So all we have to do when evaluating this query is just look at the metadata for that one Parquet file. And so even though this thing looks like I'm doing some fancy operation with 2 billion rows of data, I'm actually just reading one file, skipping to the end of the file, reading something, looking at its metadata and reporting the results, which is why I can do it in 0.01 seconds. Okay, what if I do something that returns the exact same, well, not the exact same, but approximately the same number of rows, but unfortunately is not using the partition variables? Let's say if I tried to find all of everything in the data set that was from pickup location 138. As it happens, that's about the exact same number of rows, right? So it's the subset of the data is the same size, but it's randomly distributed, right? It has no meaningful structure with respect to the two partition variables. And as a consequence, you actually have to do some work. And so this query takes 3 seconds to evaluate. All of which is a way of saying that you should try to partition on variables that you intend to query on a lot. The partitioning makes a big difference. So when you are creating data sets, if you think carefully about how you're going to partition, you can speed up your queries a lot. How do you actually do this? Excellent question. I'm glad you asked. I knew you were all asking it. Yes, I'm getting a little bit loopy. I get to that point at this get like that at this point in the workshop. Okay, here's how I would do this. Let's suppose I wanted to write my own version of the data. I want to create a new data set, and it's going to be a smaller data set that only contains, only contains the data from 2017. So I'm going to write this to a new folder, which I'm just going to call NYC Taxi 2017. But for reasons known only to me, actually, let's assume I'm building an application that is entirely, all my queries are going to be comparing I'm going to be doing analysis broken down by vendor. Like I'm constantly monitoring the performance of these different vendors who are supplying data sets. Like that may be as the function of my application. So unlike a typical application, I will be doing lots of queries on vendor name. So I have chosen to partition my 2017 data on the month because time is a variable you tend to query on a lot. But I'm also going to use vendor name. That's a variable that would be super relevant for my application. Like I know that because I have domain knowledge of what my application is going to do. So the way that the write dataset function, this is the function in Arrow that does the writing, it will, by default, it just uses the grouping variables. So I find it most convenient to just write like this. So if I just go, okay, group by blah, whatever you want to use as your partitioning variables, and then just send that to write data set. Like, so these end up being the variables that get used in your subsequent partition data set. There are some exercises for that you can work through in your free time, which I'm sure you have a lot on. We're getting to about my target time, which is good because this is the point at which I'm just going to quickly skim over a few topics and then end on a pretty picture. So there are a bunch of other things that you might want to know about, which these are all discussed in a reasonable amount of detail in the tutorial, and the tutorial itself then links out to blog posts and other things that go into ridiculous detail about how these things work. At some point in your process of learning Arrow, you're going to want to know more about data structures in it. So basically, you're going to want to know things like, okay, so data frames in R look like this. We've got data frames, they're built of vectors, that's great. Arrow has a corresponding data structure called a record batch that has arrays, and arrays have scalars in them. And Arrow has a structure called a table, and a table is built of chunked arrays, and chunked arrays are built of arrays, and arrays are built of scalars. I was like, why is it organized like this? And there's an answer to this question. There are mechanics for interacting with these objects that are vaguely similar to what you're used to seeing in R to start with. There are these low-level things that you can learn about, which I'm sure you're thrilled and excited about, that tell you all about these low-level implementation details about exactly what these things look like in memory, right? And so the way in which an array object is organized in memory in Arrow is different to how these things are done in R. And this is not the sort of thing you necessarily need to know about when you're starting out, but eventually you will want to know them. And this sort of stuff is in the tutorial if you want to know how and why are chunked arrays even a thing? Why are these things existing that put arrays together into things? There's an answer to that question. That's in the tutorial as well. Here are some accessor functions. You can build a table as a collection of chunked arrays. I know you're excited. Blah, blah, blah. You'll also at some point want to know more detail about the scalar type. So we ran into this issue earlier with integers, with a 32-bit and 64-bit integer being in conflict with each other, right? Well, how do R types get mapped onto arrow types? Like, some things are really easy. Logicals in R are basically identical to booleans in Arrow. Doubles in R correspond to float 64 in arrows. Some things are easy. Once you start putting in all the rest of the detail, there are these moments where it gets really ugly. Like, how does an unsigned 64-bit integer get pulled into R if you ever have this problem? It turns out there's a mess of things. There's a whole lot of documentation, and more importantly, there are posts that I've written that will walk you through this whole process, so that will help make some sense of these things when you run into this problem. Right now, if you're new to Arrow, you really don't actually care all that much about the internals of what all these different data types are, but this is help material is out there when you need it. There's also more stuff, again, the same thing for, there are various different types of datetime objects. There's so much weirdness with the POSIX LT type. I'm not even going to start. This part made me cry at one point. It really did. Like, just trying to understand what POSIX LT was doing. You don't need to care about this now. This is all there for you later. I do want to stop, though, and just wrap all this up, at least with some notion of what our big picture is on all of this. And I can kind of do it with two chunks of code and a picture. Here's the first chunk of code. There are some things for which we really need Arrow, right? If I am working with, billions of rows of data, and I want to do it, with R as my language, I just can't do it natively. It's just not possible, right? It's too big to fit in memory. I need some tool that's going to manage all that for me. And that's what Arrow gives me. So I've got my way of going, okay, well, I can manipulate my New York City taxi data. I can break it down into a size that, so I can do all of my data manipulation. I can do my database joins, and I can eventually, generally in that step there, reduce it to a size that is small enough that I can pull into R, right? And here's the thing. The important thing about that is that there are some things I really need R for, right? R is brilliant for things like data visualization. Here, for the New York City taxi data, in addition to having the ancillary table that gives human readable names for the for all those taxi zones, there's also a shapefile that gives me all the geographical information associated with each of those zones, so that I can draw maps, and I can use the SF package, which conveniently links to GDAL and all of those fancy geospatial things, libraries, and ggplot2 understands all that. So I can pull all these things in together, and I can write all of my native, all my happy ggplot2 code using the data that I pulled in from Arrow. So the thing is, like, for this purpose, I really, really need R. Like, I don't want to be going and learning a whole new language, right? I've got all these things I can do in R. I just want to be able to get enough done in Arrow that I can finish the job with the rest of the tools that I know in R. And because I've got that this twin need, where I need Arrow for this thing, I need R for that thing, it's super helpful to have a package like the Arrow package that will bring them together and give you this nice little preview. And that's it. That is everything I really wanted to say. According to the clock, we have like 20 odd minutes left for questions and things like that, but I don't have anything else to say other than thank you to everybody. If you have any questions, of course, please feel free to, you can sort of type them in the chat if you want, or you can ask them. I will be, you can message us, I think, send direct messages here, or you can contact us elsewhere. All the materials will remain available for as long as you like. If you have any other general feedback, I'd love to hear about it. This is sort of the first time I've actually had a go at teaching any of this material, so I would certainly appreciate any feedback that you would have. If you don't have any questions, of course, like, this isn't a university class or anything like that. You can just go. It's not like anyone needs my permission for anything. There's no additional content or things like that. But I am delighted that folks have been willing to come along to this, and I have appreciated your time. Thanks. Yeah. All right, since looks like nobody else has any questions, I think I'm going to sign off too. Just a thank you to everybody. I've really appreciated this. I'm going to go and get my kids ready for school.